I am posting the lectures. I finally got all of them, and I can post them. I'm going to try to post them here while our speaker's talking. I'll try to post them up. I wanted to introduce you to Dr. Lorenzo Berti, a fellow Italian countryman here. And he's going to be talking to you guys about nanotechnology and its relationship to biophotonics. Okay? Now, Lorenzo has spent some time at the University of Bologna, where he got his PhD in Italy. But he also spent a lot of time at Berkeley, working with several of the chemistry professors. And I think we might have even overlapped when we were at Berkeley, though we didn't know that we were both there at the same time. He's going to be talking to you about some of the exciting work also that he's been doing with Professor Kit Lam, who's a cancer researcher at the medical center. Okay. Once again, another very friendly speaker who you can interrupt at any moment and ask questions. Okay.
Okay. Well, hello everybody. It's very nice to be here. And as Marco said, I really wanted this to be as interactive as possible. I tried to pack as many information that I could, but I didn't want to get too technical, especially because there will be a lot of physics involved, and I am the first person that will definitely screw up something with this formula and thing. So there's going to be a lot of concepts, and the goal will be for you essentially to try to go home with some key concepts that you can retain and hopefully use in the future, like maybe in your career decisions and what you want to do with your future studies here at Davis. And let's just get started. So how many of you have heard the word nanotechnology? So if I pick one of you, say, did you raise your hand? Okay, say, if I have to ask you what is your concept, your definition of nanotechnology, what would you think it is?
I think of microchips and really small technology.
Really small technology. Anybody else want to add on to that? Okay, so nanotechnology comes from the Greek word nanos, right? Means very small indeed. What small? How small is small? So by definition, and this is kind of like a loose definition, small means to this order of magnitude. 10 to the minus 9 meters is a nanometer. So 1 billionth of a meter. And just to give you an idea what range we're talking about, this is like a slide that I found, and say, if a human hair is about 0.1 microns, or sorry, 100 microns, cells are smaller, bacteria even smaller, viruses even smaller. So this area right here, say between 10, maybe even like 2 nanometers to 100, 200 nanometers, is defined as being the nanoscale. All right, it's a very loose definition. It doesn't mean that something that is 9 nanometers is not at the nanoscale. Something is 101 nanometers is the nanoscale. But it defines a very specific range of size. All right? So the question for you is, why is, say, something like DNA considered the nanoscale, but something like an atom, which is more like 0.05, 0.3 nanometers, is not considered the nanoscale anymore? So why this specific range right here defines what the nanoscale is? So what's going on here? So the reason is because at that scale, and only at that scale, materials start to have unique properties. They are not big enough that you can just use classical physics to define their properties, yet they're not small like atoms, and you cannot use exclusively quantum mechanics concepts. So you have objects that behave in between, right? Meso means in between, as a matter of fact. So you have a situation where classical physics starts to bend a little bit, and materials just starts to behave funky and have like different characteristics. And these characteristics can be exploited, okay? They've been known for a long time, but it's only maybe in the past 5 to 10 years that people have really started to be able to use these concepts for material applications. And they keep going backwards. So to go back to the initial question, and this is very important because there's a lot of confusion in nanotechnology. I know many of you have seen an ad of some car where they talk about nanotechnology is going to be able to make the seat, being able to make it more washable or something like that, So you can find nanotechnology in paint. People throw the word everywhere. They just hear it and it's kind of like abused. So there's essentially 3 key concepts here, and this is one of the first take-home lessons. So one is dimensions. We already discussed that, so there's a size constraint that defines what is the nanoscale. So say roughly between a couple to a couple of 100 nanometers, more or less. The second is the mesoscale property, so they have to have unique phenomenon. So the scale defines the particular phenomenon of the material. And the third aspect of it is that you have to have some sort of control on what you're trying to do. It cannot just be something that has properties and dimension, but you have no way to control what it's doing. So that is not considered at this stage nanotechnology. You want to be able to harness those properties and use them. So, this kind of goes on in the definition, but essentially kind of expands on what I just said. Basically, with nanotechnology, you can image, so you can use nanotechnology for imaging, measuring, modeling, manipulating. You can use it for a bunch of other things. You can manipulate physical property, chemical property, biological property, but always at that scale, exploring certain unique phenomena that we will discuss, and having a certain degree of control. All right? Any questions so far? So, this is just an introductory slide, but we'll go over these properties in more details, just to give you an idea what are these mesoscale properties. And two of the most common and famous are what is called Plasmon resonance, typical of conductive material, such as gold or silver, and quantum confinement, typical of more semiconductor material. I'm not going to elaborate too much on this, but we'll definitely go back because I also have some demonstrations for you. And so that's as far as mesoscale property. And in terms of control, just to give you an idea of what we mean by control is, for example, how can you control the size? How can you control the shape? And these are only but a few examples of the things you can do. But you can make nanorods, such as this. You see about the size, about 50 nanometers, little rods. You can make things like nanohexagons. You can even make like nanotetrapods, nanoprism, and just name it. People have really found use of every possible shape and color and everything, and it just can make any type of material in many different shapes. So how do you go about actually controlling these properties? And this is kind of nanomaterial synthesis 101, but although it's really simple, it's really the way it works, and all the synthetic challenges of making a rod versus a particle versus a tetrapod essentially are all elaboration around the same theme, essentially. So you start, for nanoparticles, with a material that is insoluble. Think about a piece of gold. Think about a piece of cadmium sulfide, like a salt that ordinarily is insoluble. And if you mix the component, or you take gold shaving, you throw them in solution, they just go right to the bottom. If you make them under certain conditions, so you start growing these little seeds that are really tiny. At this point, we're talking about just a few atoms. Thermodynamically, they're not really stable, and their natural tendency is to aggregate and form larger crystals and essentially crash out of solution. But if you do the synthesis in presence of some sort of surfactant, and the surfactant could be an actual molecule, like a polymer, a long nucleic chain or not, or it could be the solvent, for example, that gives charge. As these little seeds start aggregating, you have all this either solvent, or ions present in the solvent, or molecules that you add, start absorbing on the surface. And when you reach a critical radius, these clusters that you've grown from the seeds starts to not to be able to aggregate anymore, because either they're repelled electrostatically, could be in this case it's negative, but it could be positive, or because the molecule absorbed create a steric exclusion. So they would like to stay together, but they can't because there's something that blocks them. So you can start seeing that, playing with the material, how big these seeds are, and you can play with temperature. Yes?
A quick question. How do you get this seed mode? How do you get the little seed part?
Well, as I was saying, it really depends on the material. But say, for example, to make a couple of examples, we're going to talk about gold. If you start with gold, you start with a gold precursor, like tetrachloroauric acid, so it's a soluble form of gold, and then you add a reducing agent. So you reduce the metal right in solution. If you don't have any surfactant, you just form clusters of gold, flakes of gold, they fall out. But if you have a surfactant, as they grow, they start reaching a certain size, and there it stops. If you take another common material like a cadmium selenide, for example, you kind of do the same thing. You start from a cadmium precursor, typically it's like an organometallic complex, and you heat it up very hot, and you start decomposing. and if you're in presence of like a selenide source or a sulfide source, depending on the quantum dot you're trying to make, you form these seedlings. So you can play with temperature, you can play with concentration, you can play with surfactants, you can play with time, order of addition, all these things define all these properties. And there's a lot of empiricism in this, meaning that there's a lot of theory, but also a lot of trials and error. But playing with all these parameters, including obviously most importantly the type, concentration of surfactant, you can essentially determine all the properties of the nanomaterial, the shape, the size, and so on and so forth. Another key concept that is a little bit different for those of you that have taken maybe organic chemistry or something like that, polymer chemistry is more similar in that sense, is that because of the way you make them, you don't make particles uniquely defined. So if you're making a sphere, just for the sake of simplicity, and the sphere is 20 nanometers in diameter, you're not going to have only 20 nanometer spheres. You're going to have what is called a population. So you have a distribution. In this case, is a distribution around about 40 nanometers. So you have particles that are smaller than that, particles that are larger than that. On average, they will be centered at a certain value. And what you're trying to manipulate in your synthesis is what is called the Polydispersity Index. So if you recall, I told you that size determines the properties. Ideally, you would like to have particles that have the same size, the same shape, but you can't. So what you're trying to do is to make this distribution as narrow as possible. So the population that you have has the characteristics that are the most possibly defined that you can. So you want a monodispersed population or a polydispersed population? Right, you want a monodispersed because you want to have features that are the most possibly defined. Otherwise, if you have particles that are 100 and particles that are 2, in the same mixture, you're going to have properties that are hard to control and hard to define. Of course, you lose one of the requirements of my definition of nanotechnology. It's not my definition, but it is. So let's go, further down and kind of zero in on these nanoparticles. So, how do they look? They actually look uncannily simple, And for the purpose of this lecture, I'm going to just keep the topic centered on inorganic nanoparticles, so particles that have a core that is made of some sort of inorganic material, like either a metal or a semiconductor. There's particles that don't have any inorganic core. They're called liposomes or micelles. I'm not going to talk to those because in my world they don't really belong to nanotechnology in the sense that they don't satisfy all the requirements. They satisfy the requirement of size and they satisfy the requirement of control, but they don't really satisfy the requirement of unique properties. They just have size, but don't have some of the cool properties that inorganic materials have. But just to let you know, there's other type of particles more than the one I'll tell you today. So you have an inorganic core, say gold, again for the sake of talking. You have a surfactant, which is also called a capping agent, which is the one that essentially prevents the particle to crash out and keep them suspended. And you have an interface. And the interface is essentially the part that links the surfactant to the inorganic core. And although it seems trivial, it is really not, because it's really the culprit of the whole thing. Here you have something that belongs to the inorganic world, a metal, and something that not necessarily, but most likely will belong to the organic world. It could be a piece of polymer, but it could also be a protein, a piece of DNA or something. And you have to figure out a way to stick them together so they're bound irreversibly or semi-irreversibly. And there's a lot of research essentially spent into working at this interface. And I do a lot of that. Tim, which is one of my students there, knows that very well. So what happens when you inject a substance in an organism, say a human person or a mouse or whatnot? So a drug, here also says a nanoparticle, but there's a little distinction, immediately get opsonized. So there's a series of proteins in the blood plasma, albumins, immunoglobulins, opsonins, and so on and so forth, that immediately recognize the particle or the drug, the molecule, whatever it is that you've injected, typically because of their charge, and they essentially form a coating on it. And what really defines the biodistribution and the pharmacokinetic is not the drug or the nanoparticle itself, but it is the complex, the particle and all the opsonization shell that forms around. For a small molecule, like Tylenol, say, that you can take for your fever, even when the drug gets opsonized, the size doesn't really change drastically enough to really alter significantly the pharmacokinetic. But when you have a particle, where you are orders of magnitude larger than a molecule, that makes a difference. So while a drug normally gets opsonized, and then it goes into the bloodstream, goes to the blood vessels, somehow ends up into the cell, it gets internalized by the cell, and then there's like a whole cascade of events that obviously is drug dependent, depending where the drug wants to go. With nanoparticles, when the particle gets opsonized, something else happens. And essentially, what happens is strongly dependent on the size and the charge. So we're going to go on to it, see if actually the slide's right after. I'm going to skip that one for a second. So essentially, opsonins, or in general proteins in blood plasma, just to kind of be oversimplified, tend to really like things that are positively charged. So if you have a particle that is stabilized in a positively charged form, they get opsonized like crazy. They crash out, they become much larger. You start with 10 nanometers, they become 200, 300, 400 nanometers. When they get so big, they tend typically to lodge in the lungs first. Yes?
I'm sorry, what is opsonization? What is that?
Well, as I was saying before, it's essentially a process, kind of like a generic definition of a process. There's actually specific proteins called opsonins, kind of like a class of proteins. But there's other things like low-density lipoprotein, for example, is one, or HDL is another one. Immunoglobulins, albumins, they're proteins that are just there in place to recognize anything that comes, like a foreign agent, and they cover it up. And then whatever in your body will recognize the complex, recognize something on the surface of the opsonin. So it's kind of like an innate response. And that's something that you always have to keep in mind when you give somebody a drug, especially if it's injected, because that's exactly what happens. And that's important because, as I was saying, is the opsonization that characterizes where the particle goes. So typically, as I was saying, if it's positive, opsonization is really massive, and then the particle become big, and the first place they meet is the lungs, blood vessels, and they get lodged there, and they stay there for a while. And then after a while they disaggregate, and when they disaggregate they are smaller but still big, and they end up essentially being distributed in the reticular, the RES system, reticuloendothelial system, and essentially the liver, the spleen, the lymph nodes. If they are negatively charged, the opsonization is not as massive as for positive particle, so they kind of bypass the lungs, they're not big enough, but they end up in the liver and the spleen. If they're neutral charge, like for example if you stabilize them sterically with like some polymer or some molecule that is neutral, they tend not to have this type of uptake so much, so they don't go as much into the liver, the spleen, or the lungs. However, and I'll talk about this in a second, they kind of have a hard time getting inside the cells because being neutral, there's really nothing in their surface that make them particularly palatable to cells, if you will. And so what I'm trying to convey to you, and again, that's another take-home message, is that it's kind of like a balance of things. Okay, there's no single nanoparticle that does it all, but it's the technology that allows you to make them positive, negative, neutral, a little positive, a little negative, smaller, larger, and depending on where you want them to go, you can play with all these parameters to kind of play it off and direct them more to one side than to another. And this is essentially an extension of what I just said. So this is the fundamental concept in nanoparticle chemistry for drug delivery application or imaging application. Anything that you can see a nanoparticle being essentially introduced into a living organism. This is kind of a more complex structure. You have a nanoparticle, you have things like stabilizing agents, these white things. There may be even neutral, or maybe not. They could be positive or negatively charged. These red dots represent drugs that are immobilized somehow, like small molecule drugs. This is DNA. You can imagine like putting things like, for example, they modulate some genetic expression pathway. You can imagine putting targeting agents that have a specific affinity for a cell. It doesn't matter what you put, how much you cram into the nanoparticle. What the organism sees is what's outside. Okay? So if you put a drug free drug into a system, the system sees the drug. The toxic effects and the beneficial effects and its charge, its pharmacokinetic, are all defined by the drug. But when you put it inside a nanoparticle, all the same parameters, pharmacokinetic, toxicity, biodistribution, and so on and so forth, are defined by the surface. And the size, of course, but the surface. So you can see that in a way, in principle at least, if you can make particles that are stable, you can pack them with things as long as on the surface you have something that is okay for the organism. And in a way that is a great advantage because if you can find a particle that is stable under certain conditions, in a way it is one recipe fits all. You can put in any drug you want because the toxicity of the drug is not going to change. It's defined by the particle. And when I say toxicity, I mean toxicity in a systemic sense. We're mainly concerned to anti-cancer delivery, so we are obviously concerned with systemic toxicity. Any questions so far? Did you get this concept, like the importance of the surface phenomenon? Okay. So you can use nanoparticles in many, many fields, ranging from physics, material sciences, making tiny chips, photonics, nanowires, electron transfer, and everything. We're just going to talk a little bit today about two applications that are more of interest to you. So essentially imaging and possibly even therapy. There are, as everything, advantages and disadvantages. We have talked about some of the advantages. The shape, size, surface to volume ratio would go there. So essentially you can modulate all this factor to prepare particles that have defined properties like circulation, pharmacokinetic, and so on. They tend to be stable, more stable than drugs. This is arguable, easy, hard to functionalize, but once you find the good recipe, then you can apply it to a variety of drugs and components. So at that point, it becomes easy to functionalize. They can target organs and cells through two different mechanisms that I'll show in a second, called passive targeting and active targeting. While typically normal drugs just use passive targeting, so they're just taken up by whatever physiological mechanism favors an organ versus another. They can be used for many things at once. We'll go over that too, like you can do imaging and therapy at the same time, for example. And in some cases, you can even do like in vivo imaging of biological processes real time. We'll go through all these points. There are some disadvantages. So the first to discuss is the fact that it binds to all these plasma proteins, so this opsonization mechanism, and that radically changes the properties of the particle much more than a small drug. It would happen for a small drug. And so this is critical when you prepare a nanoparticle to make sure that what the properties are not the properties of the particle itself, but the properties of the particle once it has been opsonized, because that is what defines where it goes and how it behaves. It's a little hard to avoid the reticuloendothelial, and I cannot pronounce this, guys, I'm sorry. The system that essentially constitutes all the macrophages that, scavenge out all the nasty stuff in your bloodstream, so liver, spleen, lymph nodes, bone marrow too. It's hard because they're big. So unlike a molecule that is 0.1 nanometers, these guys are at the very least 10, 20 nanometers. So it's hard to go into this place, to avoid them going to these places, if not impossible. And also there's some toxicity consideration. It's true really for everything, but in this case, because you're using usually heavy metals, cadmium, gold, toxic anions like selenide, tellurides, and everything is something that you have to be aware of. And that's why there's still a lot of resistance to actually develop products that can be used for real-world applications in human beings. So what is passive and active targeting? So how do these nanoparticles go into the body and end up going to the site of interest? So as I said, we are very interested in cancer therapy, and what we are interested in is rather than coming up with new drugs, we are interested in using existing drugs but reducing their toxicity. So rather than having them go everywhere and being toxic even where they're not supposed to be toxic, we're trying to figure out a way to exploit the properties of the particles to go more where the tumor is rather than going everywhere else. And you can do this by one of two ways. The easiest and most commonly exploited is what is called passive targeting. Imagine a tumor. This is a blood vessel. This is a tumor that grows. Tumors by nature are mutant and fast growing, and they make their own blood supplies, but they make them kind of like hurriedly and very quickly and very imperfectly. So the blood vessels that actually go into the tumor have holes in their epithelium. So if a normal blood vessels is like cell lined up, they're really tight. When it gets to the tumor and the blood vessel starts filling the tumor, there's these big holes. If you have a small drug, the drug doesn't care. It goes in here, where the blood vessels are okay, but it also goes inside the tumor. And the principle is that because the tumor has a higher metabolism than normal tissues typically, or a higher replication rate, the drug will have a higher uptake in the tumor. And that's essentially the reason why cancer patients end up losing their nails, their hair, because those are fast-growing cells. Nanoparticles are bigger. Again, we said 20, 50, 100 nanometers, so they don't go inside these little gaps where the blood vessels are normal. But when it gets next to the tumor, where they have these big holes, they fall in. Then tumors typically have a very poor lymphatic drainage, means whatever goes in is kind of like a hard time coming out. So if you give a patient a drug in a nanoparticle formulation, after say 24, 48 hours, you have that there's a significant accumulation in the tumor, much more than in other places. That's passive targeting. So essentially only works on the innate characteristic of the tumor to uptake particles of a certain size. To that, you can also use active targeting, which means that on the top of the nanoparticle, you can also put little molecules, ligands, anything that you can imagine, antibody or not, that recognize specific areas, for example, in the tumor cell or in the blood vessel next to the tumor site. So that when the particle goes through, you might have some passive targeting, but together with that, you also have some active targeting due to a specific interaction. So you kind of add an extra dimension of specificity, because passive targeting is obviously not perfect. Otherwise, there will be already drugs that will work out there. So you kind of can combine both things. And also, if you recall, I was telling you that the particles that work best, so the ones that don't get opsonized as much, they circulate for a long time, are the ones typically that are neutral, so there's no charge. But if they circulate for a long time and they have no charge, there's also nothing distinguishable on the surface that make them particularly attracted to the tumor. And so you may have some passive targeting, but then they end up not staying much. And so if you add some active targeting, you can combine the passive with some sort of specific recognition. And to give an idea of how EPR effect works, so enhanced permeability and retention effect, sorry, I didn't think I mentioned that, so passive targeting, if you see that. So this is a mouse, and in this case, you have a nanoparticle. So the same mouse, two different mouse, we're not the same mouse, obviously, have been injected at a certain time point with a dye that is fluorescent. In one case, it's just a free dye, so it's the equivalent of a small drug. In the second case, the dye has been encapsulated into a nanoparticle. So the drug goes in. This is the initial tumor. It's fluorescent because it's being transfected with a gene that essentially makes it luminous. So the small drug distributes everywhere. The green is where the drug goes, and then over time it kind of starts going everywhere. It kind of fades a little bit. At 72 hours, it's everywhere. If you take this dye and you load it in the particle, it still distributes everywhere, but then over time it starts accumulating somewhere. And the summer is essentially the tumor. If you take the organs out, you see that just concentrate on the tumor. You can see that wherever you have just a small molecule, there's not much uptake. Wherever you have the nanoparticle, there's more uptake. So that's the passive targeting, and it really works. As I was telling you, you can see the liver, you always have some. In actuality, a little more for the nanoparticle than for the free drug, for the same reason I was telling you before. Same for the spleen. So that's kind of like real action of what I just told you before.
So just a quick clarification, guys, because you saw a whole bunch of these mice with bioluminescence. In this case, this is fluorescence. So they're having to, right? You're having to excite the mice?
Yes, there's two things actually. That's a good question. So these both. So the dye that we inject, so this DID is a fluorescence dye, and it gets excited and emits closer to the infrared, and that's important because there's more penetration of light. And that's what you see when you see all the green. So say from the second picture onward, that's fluorescent. The first slide, so this one is luminescence. coming from a tumor that has been transfected with, I think, luciferase.
Okay.
And you use that as a control because when you do this type of studies, basically you implant subcutaneously the tumor, and the tumor grows. But that's not enough that the tumor is growing. You also want to know the tumor is active. So in a way, you can see this one is almost like a PET scan, because what happens is when you feed the mouse the substrate for luciferase, which is called luciferin, if the tumor is active, it metabolizes into something that is luminescent. And you can see that luminosity. So what this gives you is you have a tumor that is xenografted, but is also active. It works. It's metabolically active. And then you give the dye, and then from here on is fluorescent. So it's a combination of both.
Okay, so you guys, you get that. So you put the tumor in, you put in the luciferin, and you get a glow from the mouse, so you know that the tumor is active. That's the first mouse you see. Then the other stuff, they're having to excite the nanoparticles to give off infrared radiation. Remember, because near-infrared, red and near-infrared go through tissues really well. Remember the stuff we talked about last week, the color was green, the bioluminescence, and they were having some difficulty getting through it. They didn't have a protein that would work very well in the red or in the near-infrared. Because he's doing nanoparticles, he has more flexibility in the wavelengths that they fluoresce at. So you've got this a combination. You put in the bioluminescence to see if the tumor is there and active, and then you do the fluorescence to image where it's going. So the nanoparticles are going. And these fluorescent particles are emitting in the near-infrared. And remember, the color that you see on the mouse is just the amount of near-infrared light that's coming through. Okay?
Right. Okay. Thank you for the clarification. It's true. How are we doing with time? Because is that a clock?
No, that was that. Yeah.
Okay. But tell me, make a sign if I'm going too slow.
10 minutes, I'll take a break.
Okay. So quickly, and this is very light. Two main classes of nanoparticles are based on conducting material, gold, silver, platinum, and semiconducting material, cadmium selenide, cadmium sulfide, cadmium telluride, zinc sulfide, and so on and so forth. So what differentiates both and why is it important is essentially the way electrons behave in these particles. So in a conductor, you have that the electrons are free to move about. So you take like a piece of gold, say this one is stable as a piece of gold, and the laser point is an electron. If you apply a voltage difference between the two ends, you have that these electrons are free to move, back and forth if you change the voltage. But there's no real obstacle beside resistance, obviously, for their movement. In semiconductors, is a little different. You have the semiconductor, the electrons actually are not free to move anywhere unless there's a certain external input. That could be light, could be thermal input, could be a voltage. Once that condition is satisfied, the electron jump from what's called the valence band to the conduction band, and then they start behaving like a conductor, right? So a semiconductor is kind of like a conductor in the dormant state until something triggers it up, but a conductor is always ready to go, and that's why this which is called the Fermi level. So the energy you need essentially to make a material conductive or not in a conductor is overlapping. So electrons are free to move. In a semiconductor, they have to do some sort of jump that has to be given by some sort of external source, like light or heat. Why is this important? Let's talk about now a conductor. We'll go about the semiconductor later. So you are an electron in a piece of gold, and you have a potential between the two, like a voltage, like in a battery. The electron wants to move, it's negatively charged, it wants to move towards the positive pole, but it cannot do that in a straight line. It cannot do it in a way more like this. And the reason why it does this is because through its path, it hits things. Imperfection in the crystal lattice, it could be other atoms, anything really. There's other funky things like phonons, polaritons, and I'm not even going to try to venture myself into that. But what I'm trying to get at is that they move in sort of like a zigzag fashion. And depending on the material, the distance that an electron travels is called the electron mean free path. So how far the electron can move before hitting something in its way. Normally, in a wire of a conductor, this is really not an issue. All you see is the current flowing. But the electron mean free path has a finite value. Usually is in the order of several tenths of nanometers. So what happens if you actually shrink the conductor to a size that is smaller than the electron, mean free path. So the electron wants to move, say, 50 nanometers, but it can't because the material confines it in a volume or in a surface, in a size that is smaller than the mean free path. And that's when the mesoscale property of materials start to emerge. So you get this thing which is called surface plasmon resonance. And imagine hitting a material that has been confined to a certain size, that is smaller than the electron mean free path, with an electromagnetic field, say light, for example. And light is essentially an electric field that is moving up and down, and you have these electrons in that try to align with it, right? So you have, say, here the field is positive, so the electrons want to go there, so one side of the particle becomes negative, and the other one is positive, and they go back and forth. But say the free path is 50 nanometers and the particle is 20, they cannot move that much. So the best sort of example I could come up with is the one of, say, the tennis player or the football player that runs left and right very fast when he's doing a drill, and then as he moves from one position to another, it kind of skids with the shoes, right? So that's kind of the same thing. You create on the surface these sort of like waves, they're called evanescent waves, or also plasmon resonance, because this material at a specific wavelength create a standing wave. So it's like the string of a guitar. You hit it and it plays a certain note at a certain pitch. That's exactly the same thing. At a certain wavelength, this movement of electrons start to resonate. So if you look at it, you cannot really distinguish it moving back and forth anymore, although it is, but it's doing it at resonant frequency. And you create on the surface this resonance, this kind of like cloud of electrons where you have a very intense electrostatic, electromagnetic field. And for materials like gold, what happens is that the resonance frequency is indivisible and is about 520 nanometers, and they brought some props so you guys can see it. These are 20 nanometers gold colloid, and these are 5 nanometers gold colloid. It doesn't look like gold, but it is. Gold, you guys all know how it looks. It becomes red because around 520, 540 nanometers, it absorbs light. What's left, gives you the impression of being red, and that's how they look. And as you can see, they're suspended, they're transparent, don't have any interest in precipitating off or anything. And also, because of the resonance, the capacity of this material to absorb light is huge. So, are you guys familiar with the concept of extinction Moore coefficient? So, the extinction Moore coefficient is essentially a chromophore dependent value that gives you an indication of how much light you can absorb. And the larger it is, the more colorful, essentially, the more intense the color it is at a certain wavelength. So the bigger it is basically means that it's easier for you to distinguish it at low concentration. So even the best chromophores that you can find, at best, have an extinction Moore coefficient of the order of 10 to the 4th, 10 to the 5. So 10, say 100,000 maximum, maybe 150,000 maximum. These guys go 10 to 11. So what it means to you basically is that in terms of concentration, if 1 micromolar visually is kind of pretty much at the limit, or you can see a normal chromophore, these guys you can go down to like 1 picomolar. In actuality, you can go down even more than that. And you can start seeing why they are important, because if you can somehow couple them with something that you can detect analytically, you can see almost single molecules. And how would you see those? Well, there's properties that stem from those. So remember, size defines the property, right? So if you have a particle that is larger, the electron still cannot move all the way of the electron mean free path, but it can move a little more. So all I told you so far, the surface plasmon resonance and everything changes a little bit, and anything that touches also the surface influences this, because it's a big, intense electrostatic field. Anything that perturbs it, absorbs something on top of it or whatever it is, changes it. So you can imagine developing assays like this, and there's a lot of stuff like this out there, where you have a particle like the ones that are circulating around, that are red, and then imagine adding on the surface some sort of receptor. It could be, for example, like an antibody or an antigene. It could be a piece of DNA. And you have another set of particles that are labeled with the complementary, which could be the pathogen that they're trying to detect. If you mix them together, if the test is positive, they start aggregating because they recognize, so say the antigen recognize your antibody and whatnot. As they aggregate, not only they become larger, but it also perturbs the plasma resonance. And so they start changing color. And it's actually reversed from what is right there, sorry about that, but basically you start from a situation where they're red, kind of like the one you're seeing, and the larger they get, the bluer they get. And that's kind of like easier to remember, it just goes to where, longer wavelengths, the larger they get, at the point at which they eventually, crash down. And they brought a little demonstration that I tried only once. I don't know if it's gonna work out. And I need a volunteer for this. Actually, 2 volunteers. You guys want to be volunteers? All right. So here I have basically the particles that are circulating around. I just put like in the tubes. These are the 20 nanometers. These are the 5 nanometers. They're slightly different in color because of the size. So here I have a solution. It's just sodium chloride. It's 100 millimolar sodium chloride. And what happens is that when you increase the ionic strength of the solvent, they're stabilized electrostatically, remember? So these guys are negatively charged. The only reason why they're separated is because if they get too close, there's this big repulsion coming from these 2 negatively charged. But if you increase the ionic strength by adding salt, you shield this repulsion. So they have a tendency to aggregate, right? So you have 20, you are Mr. 20, and you are Mr. 5. And one is going to be the control, right? So you can see what happens. And these are like 2 little like that. Everything is very high tech. So why don't you guys go ahead and add, say, 1 drop of the solution? Yeah, then we're gonna, or you can come here. Yes, absolutely. One drop, no more. And hopefully it works. So let's see. Right. So we have 5 here, 5 and 5, and we have the 20 and 20. So can you guys see the 20? This one is the control. It's kind of like a reddish. That the one is kind of like a little more purplish. Can you guys see it? If you look at the 5, it's not as much. You guys see it? There's not as much difference. So again, does anybody know why? Do you want to have a wild guess on why this happens? So they're both particles, the same material, right? And they both have surface plasma resonance, because they're red. Sure. And sure. And we add something that in a way blocks this repulsion effect that keeps them suspended. And the 20 nanometers do show signs of aggregation, and the 5 nanometers don't. Or not as much. Come on, guys. Anyone guess? Tim, come on, help me out. You know the answer?
Possibly because the 5 nanometers could be aggregated, but they're not as big enough molecules.
That's a possibility, but usually the aggregation, is kind of like a cascade of events. So when you start aggregating, it just it goes downhill from there. And so it's a possibility, but you will still see a little change in color. And yet again, what is the only thing that is different between the 2 particles?
Size.
Is the size. So why do you think there will be such a difference between the 5 and the 20 nanometers? Exactly. It's the surface area. So these objects are tiny, really tiny. We're talking about, especially the 5 nanometers, we're talking about maybe, I don't know, less than 1,000 atoms. So the amount of atoms that are on the surface compared to the actual volume is humongous. And this ratio, the surface to volume ratio, obviously decreases as the particle goes up. So the 5 nanometers particle have a much more intense electrostatic field because you have a charge that gets confined into a smaller and smaller volume. I think the analogy is really not appropriate, but think in terms of like a black hole, right? Where you have like all this mass centered like in a very small volume. So you have that with the 20 nanometers, it takes just a drop of an electrolyte to shield these electrostatic interactions. With the 5 nanometers, because of the size, and also is a surface, so it scales also to the power of 2. So you have a much more intense electrostatic field. You need much more than 100 millimolar sodium chloride to shield that effect. Make sense? Yes?
How come the bottom concentration is?
In actuality, the particles do not really expire, strictly speaking, because it's gold, right? However, typically the way used in the lab is not under extreme control conditions. They are prone to bacterial contamination, stuff including algae, bacteria, fungus, and whatnot. And also, sometimes even just like a speck of dust, something that has a little charge can act as like a nucleation event, and then start, triggers like an aggregation event, and as we studied before, once it starts, it's hard to stop, and so they give you an expiration date that has no meaning that if you keep them well, you can use them for years. If you don't keep them well, you probably can use them one day, and then you're done, essentially. But, we don't use them very well, and it seems to be very stable. So the plasmon resonance of gold is really the key property of conducting material. And silver has the same thing. There was a slide, I overlooked that one, but you saw that silver has a similar thing at a different wavelength. And you can actually do some sophisticated imaging using the plasma resonance, but those techniques are way too complicated to try to explain it. Also, they're kind of not standard. There's no point. As I said, we just want to give you key concepts, so I'm just going to show you things that you can really use and remember. So gold is a metal and is dense. Right? It's like most metals are. So there's a bunch of particles out there, like the ones that are circulating around, that are functionalized with things like antibody or any other things that recognize certain type of cell surfaces. And you can use these for doing what is called immunogold staining. Say you want to see if a cell has a particular type of receptor, so you buy or make a gold nanoparticle that has the complementary to that particular receptor, whatever the complementary is. You stain them just literally by simply incubate them. You wash them out, and you use a technique like typically scanning electron microscopy or transmission electron microscopy. And because of the density of the material, they appear like little dots, like so. And this one gives you an indication that that particular cell has a certain receptor, and you can even go as far as localizing where it is on the surface or inside the cell. Sometimes that's not enough in terms of contrast, and so you can do what is called silver staining enhancement, which essentially is gold nanoparticles that gets coated with silver nanoparticles. So silver also is a fairly dense metal, and it grows them, and then you can see here essentially what happens. They become bigger and bigger. Have you guys talked about transmission electron microscopy or anything like that? No? So essentially, it's like a normal microscope, but in this case, rather than having light in the visible, you have electrons that goes through a sample. It has to be really thin because electrons are absorbed, and essentially, they pierce through, and wherever and basically they get scattered according to the density of the medium they go through. And if you have like a heavy metal like gold, obviously they get absorbed much more. Another technique that I'm just really going to go by is called surface enhanced Raman spectroscopy or Raman scattering. This one is a theoretical modeling of what I just showed you before. So this is the particle, and these yellow areas are the plasma resonance of the gold nanoparticle calculated according to computational models. And here's what you do when you tag them with some molecule, in this case, these benzene derivatives. So they are within the shell of the plasma resonance. And because of the intense electrostatic fields, they sense it, and there is this effect that can happen in a particular type of spectroscopy called Raman, but also fluorescence. We're not going to go into the details. So all you need to know is that at the surface, because of the electrostatic field, funky things happen, and one of the things is that a molecule that ordinarily you will not be able to see much, you can actually see because there's an enhancement of the property you're trying to see. One is fluorescence and one is Raman. So here will be the signal of the molecule you see by itself, but when it's close to the surface of the particle, you can recognize some of the spikes become more intense, because the way that the electrostatic field of the plasmon couples with the property of the molecule. Questions so far? So you guys have probably seen this many, many times over. This is the electromagnetic spectrum, and you have that shorter wavelength correspond to higher energy, lower wavelength correspond to lower energy, and electromagnetic radiation essentially interacts with matter in a way that is matter dependent. Okay, so depending on what you're hitting with a particular radiation, you have a certain interaction. So typically, in the visible range, you have electron transitions. So you have like that electrons from a ground state in a molecule go into an excited state. You go in the infrared, you start to be more stretching. Take like a molecule like water, you have like the bonds and like stretching. Microwave, they rotate. And the radio wave, kind of sort of the same thing, kind of on a lesser energy range. But it's just to tell you that basically the electromagnetic radiation needs to interact with a specific property of matter in order to have a property, which could be something that you look at or the plasma resonance or whatnot. The reason why I'm telling you this is because if you look at the way that our body absorbs this radiation, you see that there's like significant differences depending on the wavelength. And you all know that if you stay too much in the sun, so you get a lot of exposure to the UV, you get burnt. So that tells you that UV tends to stay on the surface. And so does the visible light. When you get to the infrared starts to interact with your water molecule, right? And so it penetrates a little more. And it makes rotate the molecule and can even heat up a little bit. And as you move to this, say towards the microwaves and then to the FM radio and so on and so forth, your body becomes more and more transparent to a certain type of radiation. But that's true for your body and not necessarily true for other materials. So I guess that what I'm trying to say is that if you stick something that absorbs a certain type of radiation to which your body is transparent, your body will not resent from it, will not have any effect. But whatever has been implanted in your body will. That's, for example, when you go to the airport and if you have like a piece of metal somewhere in your body because of surgery or something, the magnetic detector will go off, penetrates your body. Normally it's okay, but if you have something metallic, you will feel it. And that's the case, for example, with X-rays. You guys know that X-rays penetrate the body. They're ionizing radiation, so in actuality they do interact with the atoms of your body, but essentially your body is sort of transparent to it. But gold is not. And so you can actually use gold nanoparticle as a contrast agent. So down here they just use iodine as a standard contrast agent for X-ray. And here is basically trying to image the kidney. These guys are small. Remember, small particles get filtered to the kidney. I don't know if I said that. I'll say it now. Small particles get filtered to the kidney. So they end up there, and you can see them with X-ray, while a normal contrast agent like iodine, which is a dense element but not as dense as gold nanoparticles, it doesn't give you the same contrast. And there's like a lot of research trying to use these guys as contrast agents for X-rays. And another very interesting thing is what is referred to as photodynamic therapy. So let's go back 1 second. You've seen the particles. I hope you grasp the concept of plasma resonance. So these electrons desperately trying to align with the field and running like crazy back and forth, right? And they skid at the end, like the tennis player, the football player, because they can't just quite make it in terms of distance. So this is energy, right, that you're pumping into the system at a certain wavelength, 520, 540 nanometers. And these electrons are moving like nuts, right, back and forth. So where is this energy going? Do you have an idea where this energy could be going? Come on, guys. This is easy. Heat, right. You have these electrons that are just moving back and forth, and they hit things along the way, possibly. It's essentially kind of like a nanoscale friction. It's not really friction, strictly speaking, but it can see that way. So the particle heat. And when I say heat, I'm not saying heat like warm up. They heat like hundreds of kelvins. They can melt under the input. And obviously, the more intense the light source is, think about a laser, the more intense the heating is. And so this is something that among the things we're trying to do, and let's not go too much into detail, but if you have stuff conjugated into the nanoparticle, so this will be your nanoparticle, and you have things around, and you pump energy into the nanoparticle by hitting with a laser like I'm doing right now, they heat up, and the heat kind of extends around the particle. You can use this heat to burn if you want to. You can also use the heat to release stuff that is attached to the nanoparticle. And one of the things we're doing is to use these gold nanoparticles. We cover them up with drugs. And remember, the nanoparticle, as the drug absorbed, the hope here is that the body will only see the nanoparticle, doesn't see the drug, because only recognize the surface. The drug is inside. And what happens here, hopefully the movie will work. So on the left-hand side, there's a laser that you cannot see very well. Well, you can actually see anything. You see those dark spots are clusters of nanoparticle. And you cannot really see the laser spot because it was in the infrared, so it is not really visible. But you can see at some point some bubbles coming up. Let's see if you guys can spot anything. It's very dark. You see here? So that's kind of like boiling at the nanoscale, right? Because you're pumping energy with a laser and it gets really hot. That's when all you have nanoparticles. Here, the nanoparticles have been loaded with a drug that is fluorescent. So when the drug is released, you can see the fluorescence. So that's the laser. It goes onto the particle, you see, and the heat just like bursts it. And what we're trying to do is to kind of like try to take this concept, see here in the meantime the bubbles, and kind of bring it over into, ideally it will be a clinical setting. Obviously there's still a lot of work, but the idea is to do exactly that. Encapsulating a drug in a form that is innocuous and the body cannot really recognize as toxic, send it where it has to go, and then when it goes there, it can zap it, for example, with a laser, and then the drug will get released. Make sense? The concept is actually astoundingly simple, but it works, and the movies are cool. Okay. Okay, so that's it for gold nanoparticles and surface plasma resonance. If you have any questions about those, that's a good time to ask. Yes?
So is plasma resonance an example of fluorescence then?
No, it's not. Plasma resonance is in actuality absorption. It absorbs light at a certain wavelength. It does not emit anything. And so, as a matter of fact, those particles, they have a very high extinction molar coefficient, so the concentration of those is in the picomolar range, so you can see them very well, but they don't have any emissive property at all. They only absorb light.
Why gold? Why not?
There's no why. You can make it with carbon, you can make nanodiamonds, you can make nanosilver, nanoplatinum, nano anything. Just any metal can make it, as long as you have the appropriate conditions for synthesizing it. The literature is full of nanomaterial of any possible. So gold traditionally is being used because it's been known for a long time. For those of you that have been ever to Europe, you will see the cathedral and you see all the stained windows. The red is colloidal gold. It's been known since the Middle Ages. People were drinking it. People have been using it in the early of the century to inject it in joints for treating arthritis. So it's been around for a long time. So people know about the properties, they know how to make it, and so it's kind of like a natural material to start working with because there's so much known. But there's people that specialize in a lot of things. You can make nanodiamonds, you can make silver. They actually start to become fluorescent if they become only collections of a few atoms, so they have even more quantum properties as much as they shrink. So there's no why. Any material have mesoscale property at that scale, and as long as you have a methodology to make them stable in that size, you are absolutely welcome to work with any material you want. And actually, to go back to your point, you're asking me about fluorescence. I hope I didn't confuse you, because plasma resonance doesn't have anything to do per se with fluorescence. But if you put a fluorophore close to the surface, the emissive property of the fluorophore can get enhanced as a result of the plasma resonance. So plasma resonance is not related to fluorescence, but it can help a fluorophore to become even more intensely emissive. All right? So I hope I hammered in your head that with conductors, the mesoscale property is given by the fact that the electrons cannot move their mean free path. All right? So the distance they would like to move, they can't because they're confined. If you take a semiconductor, remember, you need some sort of event that bumps an electron from the non-conductive state to the conductive state. It could be light, it could be thermal energy, whatever. So in more quantum mechanical terms, what happens when you do that, well, that's actually quite intuitive. You bump the electron up in the conduction band, This is the electron. You form what is called a hole, which is essentially the positive charge that is left once the electron gets bumped up. This is called an exciton or exciton. I don't know if Marco can help me. I think it's exciton. But anyways, for all practical purposes, this is like a particle in a quantum sense. And the distance between the two charges, or the way they are separated, is called the Bohr radius. So you can start seeing where I'm going. What happens if the Bohr radius is larger than the semiconductor? So you make a semiconductor that is smaller than the Bohr radius, right? And so for semiconductor, you need an event, remember? If you use light, they form this exciton confined in a certain environment, and then the exciton recombines down. So essentially what happens, you have what is called quantum confinement, that for semiconductor is fluorescence. So semiconductor quantum dots, they're called. Their quantum property, the mesoscale property, is the fact that at that scale, a material that ordinarily will not be fluorescent starts to become intensely fluorescent because of the fact that their size is more than the Bohr radius of the exciton. So they say charge separation is larger than it can physically go. And I brought them over here so you guys can see them. This is a collection of these guys, the semiconductor quantum dots. And you can pass them around. See if you can see them without turning off the light. Oh, does this thing work? Oh, there we go. Okay. So this is a sort of UV light, so don't shine in your eyes. You can just run it around, okay, and see them before, and then run stuff out and just pass it to you. In the meantime, I'm going to keep talking. Those are, semiconductor quantum dots, essentially. What are the main characteristics? So the green line is a normal fluorophore. The blue line, the emission of a normal fluorophore, say an organic molecule. The blue line is the emission of a semiconductor quantum dot, like the one that are passing around. You can see that the green line is much broader than the blue line. Those are typically electron transitions, right? So an electron gets bumped up, it decays, and when it decays, emits light. Everything really at a quantum level is dominated by quantum mechanics. So what you see here is just a collection of many individual quantum transitions, but they're so tiny that appear to you as kind of like a continuous line, right? But as I was telling you before, with the quantum dots, you kind of quantize this thing even more, restrict them to more confined states. So you can imagine that you have less quantic state, you want to see it that way, so the band is narrower. And why is this important? This is important because if you want to do diagnostic assays and you want to be really precise at the particular wavelength you're detecting something, have these guys ever visited the CBST? Okay, so you remember there's optical benches and there's like all these little mirrors and filters and things on. So imagine that every time you have to detect a specific wavelength, you have to put together a bunch of filters, mirrors, you have to have excitation source that correspond to a particular fluorophore. It's very important to make it narrow. Ideally, you would like to have only one wavelength so that you can filter that out from everything else. So the narrower it is, it makes it simpler to detect that particular wavelength. And so here is just a collection. On the top are quantum dots, and on the top are just kind of like a standard class of organic molecular fluorophores. And you can see how much narrower they are, and you can see like the first two lines, the blue and the green. Like if you have to go and separate out this one or this one, you can see that there's definitely more room here to wiggle around because they're narrower than this. However, you will notice that as you go towards the red quantum dots, their bands become much larger. Anybody knows why? So can I start to approximate, in this case, is even larger than the fluorophore. Does anybody speculate why? So when they get to the red, the quantum dots gets larger or bigger. It's like they're gold. There's a 50-50 chance. Only these two people. It's larger, like bigger quantum dot, or smaller? It gets bigger. Okay? It gets bigger, and so as it gets bigger, this is going to be having more quantum properties, so more classical properties. Right, and so it starts behaving more like a normal fluorophore, right? So the bands starts spreading, more quantum levels to play with. However, even so, quantum dots have enormous advantages over conventional fluorophores. So even if you lose a little bit of that narrowness as you move toward the red, there still are properties that are absolutely tremendously important for imaging and application imaging. And one of them is the fact that they are virtually free of photobleaching. Photobleaching is a photophysical phenomenon. It's just kind of like very intuitive. You're looking at a cell that is labeled with a fluorophore, and you shine like an intense light like this. You look at it for a minute, 2 minutes, 3 minutes, you essentially burn off the fluorescence. So you can only observe that cell for a certain amount of time. But a quantum dot is a piece of inorganic material, right? It's like a mineral, when you say salt. It doesn't have the same organic properties in a dye. You don't break bonds or anything like that. So you can keep exciting it for a long time, and it will not bleach. So this is a very nice picture that kind of exemplifies it. These are cells where the nucleus has been stained with, I won't say which one because I want you guys to figure it out, with one organic dye or vice versa, and the outside is being stained with the quantum dot or vice versa. And then you look at those through a fluorescent microscope for a certain amount of time. So here, you see the outside bleaches out and the inside stays. Here is vice versa, right? So the inside bleaches out and the outside stays. So let's take the top row. Which one is labeled with a quantum dot? The outside or the inside? The green or the red? The red, right? Because it stays, doesn't photo bleach. Well, this one is the opposite, right? So the outside has been labeled with a quantum dot and the inside is an organic fluorophore and bleaches out. This is very important because if you have to observe something like a biological process and you want to monitor for a length of time, you want to pick a quantum dot versus an organic dye because you can observe for a longer amount of time without having any bleaching, right? Does it make sense? And also there's all the filtering issues that I was telling before, they still stay to some extent. And also another very important feature of quantum dots is given by the way they get excited. So in fluorescence, you need an excitation source. Say, imagine a fluorophore. You excite it with a light source. The fluorophore picks in the energy and decays by giving you out light again. Typically, a profile for a normal dye is something like this in terms of excitation. So this tells you that this dye, the hexafluor, absorbs light all the way from 500 to 650 nanometers. That means that if you want to have fluorescence from this dye, you can excite anywhere in this range, with the best area being here, because that's where it absorbs more light. So more light absorbed, more excitation, more fluorescence. Quantum dots, this is a 600 nanometers quantum dots, behave very differently. So this guy has an emission, we have to believe me on this, around 600 and something, 620, 730. This is the excitation profile. As you can see, you can excite this guy here. See how much it absorbs at 300, at 350, and that's the reason why, by the way, you guys can see those. You can excite them at 380, but then they emit all the way from 400 to 600 and up. The reason is because of this. You can excite quantum dots here and measure emissions here. So think about how much easier it is to excite with a single source, maybe even many different quantum dots, and each of them will shine at a different light, rather than having fluorophores, which each of them has a very specific excitation wavelength. You can wiggle a little bit, but not much, and the emission is right here, so you have to go and filter that out and everything. While these guys, you can excite at a single wavelength here, all of them at once. So that's called multiplexing, when basically you can develop assays where the instrumentation is being super simplified. It's cheaper, obviously, but also like technically simple, and you can monitor what happens at many different wavelengths simultaneously. And just to give you a very basic example, but you can kind of like bring this up and make it as big as you want. This is a quantum dot, like the one is circulating, and you excite it, and it has its own characteristic emissions. When you put something like a target, in this case is a hybridization assay for DNA, and the target adds its own fluorescence. Once the target is on, you still see the fluorescence of the quantum dot, but you also see a little bit of this fluorescence called fret emission. So some of the energy of the quantum dot gets bumped into the DNA. So you can use this as a way to discriminate if there has been DNA hybridization or not by exciting at the same wavelength. And you can imagine if you have many different DNA probes, each of them attached to a quantum dot at a different wavelength, you can use the same assay for trying many, many probes with the same setup. Any questions? No? Okay. And this is another example of multiplexing. So in this paper, these guys, what they wanted to do was to see how the lymph nodes are connected from a main draining site. So the first place where cancer metastasizes typically is through a lymph node, adjacent to the primary tumor. So if you can figure out a way to understand where the cancer goes at the very early stages of metastasis, that is a tremendous advantage because you can probably stop it just by removing those lymph nodes. And so, what they did here, they basically used different quantum dots, and they have emissions at different wavelengths, and each of them has been injected in a specific site that drains the specific lymph nodes. And then they go and image the mouse, and they see, depending on the color, they know where they injected, they know where it ends because they can follow the color, and they can excite all of them at the same time with the same excitation source for a long time. This one is taken, doesn't say, but it was taken several days later and has been imaged for many, many hours. You cannot do this with the normal fluorophore. So I hope you can kind of like start seeing where the strength of this type of materials is. Okay, I'm going to go into this for a second. Any questions on the quantum dots? Let me ask you a question. Do quantum dots heat? Let me go back to this if it can help you. Like gold does?
Yes.
More or less than gold? And why? So where does the energy of the quantum dot go? So you remember you form the exciton, and then it recombines and it gives you fluorescence. Where does the energy go?
It goes out. Some of it goes out again in light.
Right. The majority of it goes out as light. Right. That's why they're so bright.
So then it's going to heat less because there's less absorbed.
Exactly. And as you can see, especially here, which is the range where you will want to pump light in, the absorption is actually minimum. If you want to heat them up to some extent, you have to heat up here, but here are closer to the UV. So there's not a lot of penetration. So in actuality, they do heat up to some extent, but not nearly as this gold does. So quantum dots, they're not there helpful for photodynamic therapy. Gold is good. Quantum dots are good for other things. Think more imaging. Okay. Also, gold is more benign. Quantum dots are typically made of materials that are considered toxic: cadmium, tellurium, selenium, zinc, lead, and just name it. So there's a lot of skepticism about the use of those for therapeutic application because of the toxicity. Yes?
A question. So in the little demonstration, when you put the solution in the aggregate became blue.
Yes.
But then I think I found the Q dots, they were smaller because the red bands look like larger because they were smaller.
The red are bigger, yes. The relationship, so you have to think about it intuitively because there are reasons for that. But they involve solving some sort of Hamiltonian or some sort of Lagrange function. So I cannot go there with myself. So you have to think about it in terms of more electricity, if you will. And it's actually quite easy to remember because the larger they are, the more for the blue, whatever the property goes. The red, I'm sorry. So the larger the dot, the more red the emission is.
And so it was kind of opposite.
Those, yes, you're right. The golden particles, the larger they get, the more red they get. And again, there are reasons for that, but that's way beyond my because if you think about even the exciton model, it doesn't make much sense. And you will think that the bigger it is, you need more energy in. to making it the bump, but in actuality go toward energy that are less energetic. So it doesn't make any sense to me, but there's some quantum mechanics justification for that. How are we doing, Marco, with time? 15 minutes? Okay, so let's just go through this. So the last material I want to talk about is a different type of material. In this case, there's no optical property, and it's, well, we use iron oxide, but this applies to any type of magnetic material. So if you guys have ever, studied magnetism 101, you will know that a magnetic material typically is a crystal, and inside you have the atoms. They have to be paramagnetic by themselves, and usually they have their spins all aligned in the same direction. So you have many, many domains. Inside a single domain, all the spins are aligned in a certain direction, but every domain is independent from the other. When you apply a magnetic field, all the domains align in the same direction, and typically when you remove the field, they stay aligned in the same direction. So if you've ever done the experiment where you take a magnet and you put it next to a needle, and the needle gets magnetized, and then you take the needle and you can pick up another needle, right? That's because this is what happens. Like first you have a material that has the potential to be magnetic, it's ferromagnetic. You magnetize it permanently with a magnet, and then the material itself becomes magnetic. Okay? These domains have a certain size, a finite size. They're defined by these walls called the Bloch's wall. So you're starting to see here that the question is, what happens if the material is more than the size of a domain, right? So at that point, they're not more distinguished, right? There's no such thing as a Bloch wall. And you basically develop a mesoscale property which is called superparamagnetism. So superparamagnetic materials essentially are by all means magnetic. They have a magnetic momentum. They align with the magnetic field. As a matter of fact, they respond to a magnetic field much more than an ordinary material does. It's called the saturation. So it's, in a way, how much magnetism you can put into the material. However, because they don't have any residual magnetization, so when you remove the field, they just start, spinning about by themselves because there's just a single domain. There's no alignment of different domains. They don't retain residual magnetization. So meaning that you can it's kind of like an oxymoron if you want to say it in a way, but you can magnetize them a lot, but when you take off the magnet, they go back about their business and they don't aggregate and have any properties like that. I actually have some if you guys want to see, but in biomedical sense, we call these ferrofluids. So you have a suspension of this particle, it's colloidal like the gold, but in this case it's magnetic. And they give you like a clear solution and everything. If you put them close to a magnet, they go to the magnet, but when you remove the magnet, you shake them up, they go back. And in actuality, this is kind of the behavior of the larger ones. The ones that are smaller, they don't do this in the sense that they don't really aggregate, but they have properties like this, where basically that's a big magnet. You guys see it? You see, so where the magnet is, it forms like a line. You can tell that there is some attraction, but you don't see any like crashing out like you see it right there, right? So the particles stay suspended. And that's very important for biomedical applications because you can start seeing that you can inject a person with a magnetic fluid. You can use a magnet, move it around, right? Or localize in a place, but they don't form clumps or anything. So they maintain their identity. You don't retain any residual magnetization, but you can still guide them somewhat to the body. Okay, I have actually some demonstration stuff here, but we'll see if there's time. So you can use it for doing this thing, which is called magnetic drug targeting, which is essentially what I just said. You can inject these particles either by themselves or loaded with a drug, and they start circulating. But in this case, you have an extra possibility of controlling where they go because you can use a magnet. Other particles, you rely either on this passive targeting, so wherever they go, or you can add some targeting ligands. Here you can also use a magnet, and depending if you inject them in a vein or in an artery, you can intercept them before they go through the heart and through the lungs, so you have some advantage there too. Like here, for example, they show you if it goes through the artery, that feeds the tumor. These dark areas are nanoparticles, magnetic nanoparticles. They accumulate at the tumor, but if you inject into the vein, not as much or almost nothing, because they get intercepted by other things, like the liver, the spleen, and so on. All those rules apply to these guys too. And there's been a lot of effort using them as contrast agents for MRI. Actually, these are data that really come from a clinical trial that unfortunately failed. But the idea, this was for breast cancer, and essentially the idea is that when you have breast cancer, again, the first place where the cancer spreads is one of the adjacent lymph nodes. And typically what they do, once they remove the lump, they also take off a bunch of lymph nodes, and then they do biopsy and they see if it's spread or not. And sometimes they remove the whole lymphatic system. It's really invasive. So the idea is maybe there's no need for doing that. If you can figure out a way if the cancer is spread already to the lymph nodes. And so the idea is that once the lymph node is healthy, there is uptake of the nanoparticles. It's kind of, the lymph nodes is kind of like one of the sponges of our body, and they have kind of like a structure that allows the particle to get trapped. So the particle go in and stay there if the lymph node is healthy. If there has already been invasion of the cancer, all the good stuff in the lymph node is gone, and the nanoparticles cannot stay there anymore because there's no space for them. They've been invaded by essentially metastatic cancer cells. And so magnetic particle results typically in a region of hypocontrast, so they appear darker. And so you do a scan before and a scan after. So this is before injection and after injection. This is the lymph node. It's before injection and after injection. This is the lymph node. And the magnetic particle give you a dark area. So here, you identify the lymph node, you inject the particle, it gets dark. That means that the lymph node picks up particles. It means that it's healthy, it's okay. Here, it doesn't pick them up. It means the lymph node has been invaded. So that means that the cancer is already drained through the lymph node, and so it's already metastasizing. And then this patient will have to, undertake surgery and have the lymphatic system removed and so on and so forth. And another application of magnetic nanoparticle is hyperthermia. So think about the gold nanoparticle for a second back here. Remember how you pump light because you have this plasmonic absorption and all the energy dissipates into heat. The same thing you can do with these guys, but in a magnetic sense. Okay, so the particles are stable and they're suspended and everything, but they're like tiny, tiny little magnet. If you apply a magnet, the spins align, right? So they're normally floating in solution and moving around, the spins move around, but when you apply a magnet, ding, they all align. If the field that you're applying spins itself, is an alternating magnetic field, they try to align with the field. The faster the field goes, the faster the spin. And all this energy essentially goes into heat. And if you can combine magnetic targeting, so moving the ferrofluid in the body and localizing a certain position, and then zap it with an alternating magnetic field, not only you localize it, but you can also heat it. And in essence, this is pretty much how the system looks. It's like a coil where you pass current. The current generates a magnetic field right here in the bore of the coil. And if the current is an AC current, so it goes back and forth, the magnetic field goes back and forth, back and forth, back and forth. And if there are particles in there, they heat up. And if you remember the slide before where it says that radio frequencies usually goes through the body, no problem. If the magnetic field is modulated in the radio frequencies, your body is okay, but the particle will heat up. All right, and you can use the micro frequencies, you can use microwaves, and you can use radio frequencies for doing this type of things. What I wanted to show you, I'm actually going to skip here for a second, and hopefully it will work. I'm not sure, no guarantee. How much time, Marco? 5 minutes, maybe we can do it. Because a lot of the things that I've been showing you today are sort of, that's what's happening here, sort of like sci-fi.
The network may or may not.
I don't think it's coming in.
Yeah, I was having problems with it.
Yeah, it's not coming in. Oh well. you guys can go and check it out by yourself if you're interested. So there's all the things I showed you today. You know, they're very sci-fi in a way, and there's still no real-world application. You cannot go to the hospital and get treated with hyperthermia or with plasmonic heating, but it's getting there. And there's a lot of studies doing there because the technology works, but it's still in its infancy, right? We're still trying to understand how this material works, especially we're trying to understand how you couple many properties of these materials with, for example, biological functions, like, you know, attaching a protein, attaching an antibody. There are two companies, and if you guys have time, go and check them out. One of them is called Nanospectra, and one is called the Megaforce. Megaforce is out of Germany. Nanospectra is, I think, out of the Bay Area. Nanospectra has a phase 1 clinical trial, gold nanoparticle suspension for treating head and neck cancer. And you inject the patient, the patient comes back a couple of days later, and the particle accumulate through passive targeting in neck tumors. They're usually very localized and they metastasize not much. And then they go in with a probe that is essentially a needle, and on the tip of the needle there is a very powerful near-infrared laser source. And they light up the particle heat and they essentially burn the tumor. They don't really burn it in the sense you imagine, but they go above a threshold temperature where the cells essentially starts dying and the tumor is reabsorbed. The other company in Germany do it with the magnetic ferrofluids, and they treat glioblastoma, which is essentially an incurable type of brain cancer. In that case, because it's so hard to reach the brain, they actually inject the particle directly in the tumor, like in a cannula, and the patient stays with this particle for weeks, and then he comes back every other day or every 5 days or whatever it is. He goes into this machine, which is essentially like a big version of what I just showed you here, and like a big gigantic coil, and they zap the patient. Actually, well, I had this one. They zap the patient with a magnetic field. The particle heat up, and the tumor essentially again gets burned from the inside out. And they're starting to couple this approach also with the particles that are imbibed in drugs, essentially. So the technology is starting to get there. Maybe it'll take 5 years, 10 years, but it's very exciting because that's the direction that these materials are going. From being academic curiosities on to being real materials that can actually be applied for real-world application in therapy and diagnostic. And one thing just to conclude is that all the things I told you today can be combined. So you can make a magnetic particle that is coated with gold, so it's magnetic and plasmonic. You can make a quantum dot that is coated with magnetite, so it is fluorescent and magnetic. It can be fluorescent and magnetic and plasmonic, you just name it. And you can combine them any way you make it. So the whole is like, do you have the necessary synthetic tools so that you can make these layers? But you can imagine, anything you want in that sense. So just, it's like having a Tinker Toy set, and you kind of play with things. You can tailor-make a material to your needs. So go back to the question, why not carbon? Why not? Sure, you can use carbon or anything else you want. You can come out with an application that combines all these properties. More power to you, because that's exactly one of the properties, one of the advantages of using these nanomaterials. So I hope I was able to give you an overview. Didn't confuse you too much. If you guys have any questions, even in future days, and make a slide with my name, but Mark, I know was out to contact.
So why don't you just write your email right there under?
Yes, sure. Well,
Let's please thank our speaker.